So thanks for the opportunity, Christine, to speak at this meeting. I want to cover some ground here, partly historical and motivational for what I'm doing. So this work is being done partly, I have a PhD student, Pragati Gupta, and we're collaborating with the group of Andrea Morello at the University of New South Wales on experimental realizations. So our theory paper came out in Physical Review Research this year, and then we have a paper on the archive with the experiments, so you can look everything up. It's a recent paper. And I'm just going to talk to you generally about kittens, cats, combs, and compasses. I'll define all the terms, and then lead into what we're doing with Schrödinger cat states on a single antimony nucleus. Okay, so just to give you some history, we talk about, you probably hear about this now a lot, is cat codes, cat states, and all this stuff. Just to make sure that the concepts are clear. The coherent state, okay, you can see up above, it says 10/BXQ-G3T. So I just put down the short DOI. So if you go to doi.org and you type that in, you'd be able to get the paper. Just a quick way of giving references. The paper up in the upper right is Schrödinger's paper where he solved his eponymous equation and was able to show that a Gaussian wave packet would oscillate back and forth, follow the center of mass motion, wouldn't disperse during the dynamics. And so in a sense, the coherent state was really done by Schrödinger earlier on. And he pointed out that the idea of the coherent state is tied with a notion of classicality, that we often think of the coherent state as the closest mathematical description of a classical state. And then that Schrödinger cat on the left is going to come up again and again. In Schrödinger's original paradox about the cat, the idea is that the cat, it's not that the cat's in a superposition of being alive and dead, but rather the cat is entangled with some nuclear decay that causes a poison gas leak. So in the original Schrödinger paradox, it's an entangled state. The cat's entangled with that. But over time, we now talk about Schrödinger cat is a superposition of dead and alive, or superposition of two coherent states. And I'm not the language police, so whichever version people want to say is okay with me, but I just want to be clear about it. The Nobel Prize that went to Roy Glauber recognizes his role in equation 1, you can see on the right, that's the coherent state. In this case, it's written as a square root of Poisson distribution multiplied by Fock number states. And so the coherent state that he did, the coherent state, that concept was done by Schrödinger, but Glauber was the one who recognized that the coherent state would describe laser output, describes dipole detection, and so on. And so kind of gives you the context. And then what happened is the idea of superposing two coherent states didn't come up until, on the left you can see a paper by Dodanoff, Malkin, and Manco. And so this is the first paper I can see that talks about a superposition of coherent states. This is done in a mathematical physics way. So I won't go through it, but essentially they're tying this with group U11, UN1, and so on. That came out in 1974, but the paper was largely forgotten by most of the community. So even though this is really the first instance of cat states I find in the literature, it's not well cited, it's not well known, and I think it's because most people who work with cats don't think about looking up mathematical physics work. But it's a nice paper. On the right, so then the next time it appeared was a paper by Jared Milburn back when he was a postdoc at Imperial College London. And he has it appear, I think that you can see, this is an extract, I think, of figure 8 from his paper from 1985. On the right, that's the cat state appearing as a superposition of two coherent states represented in phase space. And on the left, that's a superposition of 4 coherent states, and that's actually the compass state that I'll talk about shortly. So it came up, but he didn't write anything about it. In Milburn's paper, he was much more interested in representations of the dynamics. So when he saw some really interesting things, it was not the focus of the paper. It was there. And I remember I was his postdoc soon after, when he was no longer a postdoc. And there was Yerke and Stoller a few years later. Actually a year later, they saw the paper, and then they thought, gee, figure 8b is really interesting. I think I'll write an article. So that Physical Review Letters article is all about figure 8b. And then I'll tell you later, Zurek has a beautiful paper in Nature in the year 2001, and that's about figure 8a. So it's kind of an interesting story where the subfigures two subfigures became a phys rev letter article and a Nature article. So there's a lot in that one. It's worth reading. So the idea of the cat states was kind of science fiction for a long time, and I know I'm old enough to remember working on that in the old days, and you always get a chuckle because everybody says, you know, what are you doing? You should be working on something useful like squeeze light or whatever. And then, but then over time, these things started to pop up. So the first experimental paper on the cat wasn't quite a cat. So you can see the title is about kittens, Schrödinger kittens. And the idea is that a cat state is a superposition of two coherent states that are far apart. They're Gaussian. So if you have a few standard deviation separation, they're almost distinct. And the kitten has an overlap. This one, this paper that they did is really a photon subtracted squeeze state. And then they do a fidelity argument to say it's close enough to a cat. To me, it's kind of like, I like the paper a lot, and technically it was very challenging, but it's kind of like the argument that if it quacks like a duck and walks like a duck, it's a duck. So fidelity-wise, it feels like a cat or a kitten, therefore it is. But that wasn't a scalable procedure. And then over time, and we've just been hearing talks about these superconducting systems, this paper that came out in Science in the year 2013 from a group of Devray and Sholkoff was with theory by Merahimi, Girvan, and others, really was the experimental result that showed that cat states are viable experimentally. These systems are so good that you can, for me as a theorist, I can write down the theory and they see, what they see is what you write down. It's kind of exciting. And it's actually interesting. It's a 100 photon Schrödinger cat state. So the amplitude of the coherent state is the square root. Square root of 100 is 10. And then you have one at 10 and one at minus 10, and the standard deviation's around 1. So it's like 20 standard deviations apart. It's incredibly good. And you can see in the abstract, they talk about 111 photons. And usually, I find we scientists tend to use hyperbole and exaggeration, and this is a rare paper where the title is more modest than the actual result instead of bragging about it. So that was a beautiful result. Okay, so cat states became viable. And then this one I thought I'd put up. If you can make a superposition of two coherent states, why not make a coherent state in two modes and make a superposition thereof? You can see here there's two microwave cavities. And so the title's called The Schrödinger Cat Living in Two Boxes. You can see down in a blown up part of the abstract on the left, it says, has been known as the entangled coherent states. Here's a shameless plug of an article I wrote once, Review of Entangled Coherent States, that gives a 45-year history as of 2012 on the subject. And so the entangled coherent states is what they realized there. And so being able to do that's important. If you've heard of cat codes, the superposition of two coherent states could be a logical 0 or 1, depending on the phase. And then if you can go to two of them, then you have two qubit, like my shirt. You get an entangled state, so entangled qubits out of it. So that's what they get. Incidentally, I point out in this article that the first entangled coherent state appeared in 1967, but I mentioned to you that the first cat state came out paper was 1974. So and that was actually a paper by Aharonov and Susskind in 1967, where they tackle, it's kind of like a particle physics predisposition for superselection rules. So it's the paper's on why charge superselection doesn't hold but seems to. And so the entangled coherent states first arise in that paper. It's all in my review paper. Okay, so the cat code, historically the first mention of a bosonic cat code, a bosonic code was in the work by Ike Chuang when he was a PhD student with Yoshi Yamamoto at Stanford University. But in terms of using the code as a cat code, the first paper that came out on that was from the group, from Jared Milburn's group, was Bill Monroe and Paul Cochrane worked on this, and they said macroscopically distinct. So it's interesting. In nature or science, you're allowed to say cat and kittens and all this stuff, but the American Physical Society language police don't allow you to use nice terms. So they weren't allowed to write cat, so they have that complicated story. And then they have a bosonic code for some purpose. And then I contacted them soon after, and I said, hey, one qubit's not enough, you need two. So then we put the entangled coherent state in. So we have the cat and then the two-mode version of it so that we could work with, we could essentially do quantum computing with cat codes. Not long after, there came a really nice paper, which I'm sure a lot of you have heard of, by Gottesman, Kittens, and Preskill. It came out in 2001. And I'm just going to walk you through a little bit of their paper just so you understand a bit. It's important for this workshop because this is the first paper to talk about QuDits. So this is the original. Interestingly enough, the paper is called Encoding a Qubit in an Oscillator, but I read the paper when it first appeared on the archive. It was called Encoding a QuDit in an Oscillator, and you can check the archive and go to the first version, but the American Physical Society Language Police wouldn't allow QuDit in the title. And these guys don't care enough to fight it. So the later version and the published version says encode a qubit, but if you go through and you can see on the lower right, it says construction of the 3 qudit gate. A lot of the paper is about QuDits. And then I got into QuDits early, motivated by this paper. So it was an important step. The idea of their paper, it's kind of like what you see here, the zero bar, cat zero bar, is if you say the qubit could be a superposition of 2 coherent states, why not go nuts and do a superposition of infinitely many? So say, let's consider a superposition of infinitely many, infinitely thin Gaussians and call that logical 0. Now, mathematically, it's physically crazy, but it's also mathematically crazy because the 2 limits, the limit that the Gaussian goes to 0 with and there's infinitely many, don't commute. So it's kind of like an undergraduate mathematics exercise, why it's not well defined. But these guys are not stupid. They did it that way, but it gave them by doing the math wrong, it gave them an intuition into some really good work. So they write down that infinite superposition of infinitely thin Gaussians, logical 0. Then the logical 1, I call that the comb. So now you know why there's the comb. So it's a comb. And then another comb midway between is the logical 1. You can do, because these are infinitely thin, you could do as many combs as you want, just where the teeth are between the other. That's where the QuDit story comes in. So just a comb, each comb being displaced by half the width would be a qubit. If you displace by a third, it'd be a qtrit, and so on. Incidentally, the same math comes up with frequency combs that are used for locking lasers. So it's so if you learn this or learn that, you've kind of learned a bit of the other. Then if you take the Fourier transform of this comb, it's a comb. Now you can see where the limits don't commute, because on the upper right, you can see that if you take a logical 0 and you say, well, it can't be infinitely long and infinitely thin, so you take finitely many, then you get a Gaussian wave packet around a superposition of Gaussians, and then when you do the Fourier transform, the 2 widths change, right? So you kind of swap your 2 widths in doing that. But we'll go back to the ideal. So in the ideal case, the Fourier transform of a comb is a comb. And then the thing is that the separation of the teeth is now, instead of being alpha, it goes as 1 and alpha. So the more distinct you make your teeth, the Fourier transform makes them less distinct. So there's a bit of a trade-off. And this kind of approach is done, last time I checked, various companies like Nord-Quantique in Canada, Xanadu, and others are doing this. So trying to use these compromised comb states is an important strategy, one of the approaches to doing photonic quantum computing. And you could do QuDit stuff. So the QuDit side hasn't been well studied yet, so if anybody, particularly students here, are looking for homework, it's, there's good exercises in taking what's done with GKP codes and then extending it to QuDit cases. So I can't help but give homework to people. This is the compass state that came up with Zurek. So it's called a compass state because instead of 2 coherent states in phase space, it's 4, and you have 1 on the east, 1 on the west, 1 on the north, 1 on the south. So the superposition of 4 coherent states on a circle is called a compass because of northeast, southwest. What you see between near pairs are these elliptical lines. So the fringes in phase space correspond to the interference between neighboring coherent states. But what Zurek points out is in the middle of in the center of that diagram, so the center of the circle they lie on, you get some kind of a speckle pattern. And the speckle pattern gives you kind of an isotropic character that whatever marginal distribution you take in phase space to look at, what is the position distribution, momentum, or some linear combination, you can get what he calls subplanck resolution. Subplanck is not what cosmologists would talk about, but rather subplanck in this case is areas that are smaller than coherent state. I won't go into it. I mean, I can always answer in questions, but seeing the subplanck structures, you have to take marginal distributions of this. So resolving subplank structure doesn't happen. The phase-space quasi-distribution is not physically discernible, but you can do a tomography to reconstruct it. So there's kind of certain safety latches to make sure you don't see really weird things. And that was the one I said, that was figure 8B, 8A out of Milburn's paper. So this is the Nature paper that came out of another one of Milburn's subfigures. Okay, now I'm going to connect this all to QuDits. And so for this, I just wanted to tell you the story. So the coherent state had certain properties that I mentioned at the beginning talking about Schrödinger's work, that it followed the center of mass motion, that it's non-dispersive, and I didn't mention, but it's also a minimum uncertainty state. And so back in 1970, there was work by Arecki, Kittens, Gilmore, Clowder, I think there was one more, and they kind of asked the question about, can we apply the coherent state notion to atoms, to electron motion in atoms? And they built up a story, and it was essentially using the group SU2 that we've heard about today. And then Perelimoff took that idea, and then he wrote a beautiful paper in Communications and Mathematical Physics where he says, just give me a Lie group, and I can make a coherent states for it. So the Lie group gives an action that takes this whatever state, like you can think of a spin-up state or whatever, and then it just kind of rotates it. Or if it's SU11 that you use for squeezing, then there's a Lobachevsky or hyperbolic plane, moves it along. So he essentially just used the idea of group actions to define what the states were. But the nice thing about this, in this case for SU2, there's a block sphere, and then you can see 2J plus 1 levels. So instead of using like what we teach undergraduates with principal quantum number, orbital angular momentum, et cetera, with a ladder of levels, we can go to using a representation over coherent states. So the coherent states are well posed. This is actually, I'm going to throw in one gripe, is that people keep talking about continuous variable systems, and they often mean oscillator. But if I use a coherent state representation for QuDits, it's also continuous variable. We're at a QuDit workshop, so if anybody ever says continuous variable, blah, 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 say, oh, are you talking about QuDits? And I'll say, what? That's not continuous. And you can surprise them with how insightful you are, that you can tell them why they're not using the term correctly. Okay, so back when I was Milburn's postdoc, I was interested in his paper too, so this was also inspired by it. And in this case, I thought, well, I guess I was kind of born with QuDits in my mind. So I started thinking, how can we, is that idea that led to Yerke and Stoller, led to Zurich's paper, do we really need to think of infinite dimensional Hilbert spaces and oscillators? And the answer is no. And so I started thinking, okay, why don't I just turn it all to SU2? And in this case, back in those days, we couldn't do plots on the sphere, very basic. So this is all stereographically project sphere, but essentially there's a coherent state. And then this is a phase-space representation. It's a Q function or Husimi function. And then there's the cat state popping up. So this is the spin cat state. It's also a noon state, as I'll point out, and there's articles about this. And then over time, these are just some other articles. When I get bored, I just kind of think, okay, what do we know about oscillators? I think I got some spare time. I'll work it out for some other Lie group, just following Perelimoff's idea. So these is kind of a hobby of mine. Okay, so what's interesting, not long after I did that work, there was work that came out of Boulder, Colorado. You recognize Wineland's name, Nobel Prize winner on that, and so Bollinger et al. They had a paper and they said, they considered the following, and this is related to the whole field of quantum sensing, kind of says that, if you want to double the precision of, say, a clock, I'm going to speak very loosely, then you have to quadruple the number of atoms. So you have this shot noise story that says that there's a quadratic overhead in being able to enhance your precision. And they said, what if you could take a clock that's based on an ion trap, but instead of every ion being in a superposition of ground and excited, it's a superposition of all ground and all excited. And so they wrote that down. Then in equation 1, they invoke permutational symmetry. So as long as your ion dynamics are all permutationally symmetric and your environment is, which is very hard to engineer, then you have that. But if you know, and this I think came up today, but if you know Scherval duality, you say, well, I have n ions, so it's a tensor product of n two-level systems. And then, this came up when we talked about multiplicity and benchmarking. As you say, yes, but this is just the superposition of different permutational symmetries that give multiplicity, and then different irreps, different qudit irreps. And then you say, yes, but I guarantee that the physics in my ion trap is permutationally symmetric. You pick out the permutationally symmetric case. But what they wrote there, and you can see this cat state, is exactly what I was writing about before. It's the same. What they got in the ion trap is exactly the same as this superposition. So it was very interesting for me because I was kind of thinking of it more as mathematical physics. I was actually a referee of this paper when it came out. So I studied it very carefully and thought about it, and I started to realize, why is it so good? Why do you get the quadratic advantage? And in my mind, it's because they made a qudit cat state. So that's how I think about it. Nobody else thinks about it that way, and that's okay. But in my mind, that's where I get the intuition. Okay, now I'm going to jump to now I want to leverage from there to the cat state that my group were doing in collaboration with Andrea Morello's group at the University of New South Wales. So, and as I said, the experimental results are all on the archive. It's on the archive as of April. And so let me tell you this. Now, again, if you teach undergraduates or you take a class, they always say, don't think about spin as being really the electron spinning. And I always go around feeling guilty that I do think of that. So I just think, to me, the electron spins, it's just, it takes 4 pi to get itself all the way around. So I don't mind thinking about a universe where it's 4 pi to get around, and I'm okay to think of it as real. So if you accept this way of thinking, then to me, the nuclear spin is really the nucleus spinning. So to me, and in the experiment, we're able to get antimony in silicon, isolate it from the universe. I'll explain a bit how. And then it's a high spin nucleus, so the antimony we use is a spin 7/2. So as a qudit, it's a q-octet, an 8-level system. So to me, that antimony nucleus is really spinning inside the silicon. And what we want to do is make it in a superposition of spinning one way and spinning the other. So it's just, the nucleus is just a spinning ball, and it can spin the opposite way, and we want a superposition. But we want more than that. We don't want to just make it a superposition of spinning this way and this way, but we want to be able to devise a system where we don't know what axis it should be around, right? So that it's always easy to pick a direction by applying a magnetic field, but we say first apply the magnetic field, then call me up and tell me, make a cat state around some axis. Okay, and so the middle picture is supposed to be the superposition of spinning in 2 directions. And then the way we actually do it, and again, it helps to think of the nucleus as a ball, is that we take the ball, we stretch it, and then we have a torsion. And then the torsion on it is causing, essentially it's a nonlinear rotational effect that torsions it, and then, classically, if you take a ball and you twist it, it's just going to twist up and eventually break. But quantumly, you twist it, and it will turn into a cat. So that's the idea. If you get into literature on this, there's the Kitagawa and Ueda paper, 1993 Physical Review A, that talks about 2-axis counter-twisting. So if you know about 1-axis twisting and 2-axis counter-twisting, that's a mathematical way. But in my mind, I see this ball being twisted. And so we want to be able to do it. We use an electric field gradient to be able to stretch it out of shape. It's attached. I'll show you how it attaches to the silicon, and then we're able to get that effect. On the right, you can see some mathematics. So the Hamiltonian in the influence of the electric field, that's that curly V alpha beta there, this is the distortion that takes place that caused the nonlinear twist. So on the right, you can see a Hamiltonian that involves quadratic terms with respect to spin. The quadratic terms with respect to spin is interesting because it means that is it a spin system? Well, the Hamiltonian doesn't live in SU2 algebra. The Hamiltonian lives in the SU2 algebra, but then the action is not in the SU2 group. And I'll show you later it turns out to be SU8 dynamic because it's a q-octet. And then that understanding was really important to devise really good control schemes for the system. Okay, so this is showing that we could pick a different axis. And then this is the tie-in with the 2-axis counter-twisting and the 1-axis twisting. And what you see here is we have in our system, we have the nonlinear term due to the electric field, and then we have a magnetic field, that's the gamma I dot B naught. And so what's happened is there's a linear magnetic field and a quadratic term. The effect of that is that the ladder of energies is no longer equally spaced. It goes from a linear spectrum to a nonlinear spectrum. And what happens when it's a nonlinear spectrum is we can drive different levels at different frequencies. And so this is the quantum control technique. In fact, thinking about it this way is really nice as a bridge. Instead of thinking of it as an SU2 dynamic, we actually recognize through doing this that it's SU8 mod U7. Actually, when I first started collaborating with Andrea, I went in the lab at University of New South Wales, and they were showing me the system, and I said, oh, wow, how many control parameters do you have? And I was hoping, I hope the number's 14. And sure enough, the number was 14. And so they had 14 parameters. They said, we have universal control. Why is 14 so important? Because it's SU8 mod U7. SU8 has 8 squared minus 1 equals 63 parameters, and U7 has 7 squared, which is 49. And you can check on your calculator, 63 minus 49 is 14. So when they told me they had universal control with 14 parameters, I thought, okay, great. They are really doing, then I can devise a control scheme because it really is SU8 mod U7 dynamics. So it's important. So what I'm telling you about the mathematical physics, sometimes it can be really important when you go in a lab and you look at things, because if you know this stuff, you can think of good ways to do stuff. That's what I find. That's the nonlinear spectrum. And so the way we do it, originally the idea to make a cat state, and this is done in atomic systems, is you kind of say, let's put everything at the bottom of the ladder, and then let's lift it up one rung at a time. But if you're really good at if you think of the quantum control stuff, like in the quantum world, you don't climb a ladder to the roof. You kind of do everything, you do in a superposition of all. So each step of the ladder is a different size step, so different energy. And then if you want to climb a quantum ladder, you do all the rungs at once. Much more efficient. So once you realize that, and then you design the scheme, the dynamics is given by SU8 mod U7, and then physically it's just climbing the ladder every rung at the same time. So it means that we can do the dynamics quicker than the previous obvious, which is do one rung at a time. Okay, and then what we do here is we characterize it. So remember I told you before about a cat versus a kitten. And so the kitten had small overlap and the cat had big overlap. There's work that Wolfgang Dürer's group in Germany did, the 10/F3S MC7 is the reference to it. And essentially they're using some kind of Fisher information argument. So the idea is you want to make somehow objective how cat-like versus kitten-like it is. We use their method. And then over here, if you get their parameter NR effective bigger than about 4, it's cat and not kitten. And you can see there we picked some nuclei. So 75 arsenic is spin 3 halves, 2 antimony isotopes, 121 and 123. Bismuth is the best one you can get out of the periodic table, but we don't work with that because, and I'll explain in a moment, there's a preparation problem. And so, but if we work with those nuclei, we argue that spin 5 halves and bigger is cat-like. So we want to make sure when you work with QuDits, you're limited how far apart your coherent states can be. So you kind of need an agreed, communally agreed rule on what's a cat versus a kitten. But you can see it in this picture. So you can see a cat at spin 1. The coherent states are the blue superposition of coherent states. And then spin 5 halves, you can see how far apart the coherent states are. Spin 7 halves, spin 9 halves. We work with the spin 7 halves. So visually, you can see it's a cat, and mathematically, we can put in a good argument for that. Here's the way, this is a concept for how the system works. And so this is there's the silicon substrate. There's a single antimony nucleus, that's the red dot, antimony 123. And then we have a set of wires, electrostatic gates to be able to stretch the nuclear ball. And then we have the microwave antenna. The microwave fields drive the different transitions. And then we also have a single electron transistor. And so this is the key point. And why we use antimony and not, say, bismuth is because we have a, including questions, or? Okay, 8's better. It's a Q octet, but yeah. Okay, I negotiated one more minute. Okay, so so the point is that here's the way it works, that the antimony has 5 outer electrons, and you can see here 4 will bond to the silicon. And the effect of the electric field is to distort the silicon so it stretches that ball. So we make use of the electric field gradient to get that distortion that will stretch the nuclear ball. And then, but what we do here with the electron, there's a 5th electron. We use the electron in an electron spin resonance method to prepare the nucleus in the state we want. Then we yank it off, we ionize it, and then when it's ionized, that antimony doesn't even know there's a universe anymore. It's decoupled from the universe. The coherence times are much larger than anything we ever care about. And then when we're ready to read it, we put the electron back on. Okay, so you see the ball, the 4 outermost electrons grab onto the silicon, and then we just ionize it. It's an isolated ball. We play with it to make a cat, and then we put the electron back to read. That's the way the system works. Okay, then we go down to, I'm going to just put these slides up just to show you that if you ask questions, I can answer if you want, but this is kind of the readout. These are standard electron spin resonance techniques that we can go through if you want, but nothing we invented. It's just, I just put up there for completion. Okay, now here's the experiment. So this is in our paper from April, and I'll just walk you through some of the stuff. So on the upper left, that diagram, you can see a B1 and a B naught. So it's kind of an NMR, nuclear magnetic resonance technique. We've heard about that technique today. And so it's got different lines there that have, there's a DC magnetic field. There's a line, microwave line that carries a magnetic field that is AC, magnetic resonance technique. And then we also have electric field lines. And then the pink on the lower left is the SET. So that's kind of showing you the system I showed you before. Conceptually, that's what we do. You can see a nice picture with the antimony attached to 4 silicon over there, and then the way the energy levels go. The fact that it's nonlinear means that we have different frequencies, F1 to F7. We make sure everything is spaced out enough. It's close to linear, but we have the resolution in terms of microwave control. So all our control, remember I told you about climbing up a ladder every rung at the same time? What that turns into is just having multi-tone control. So we have all 7 frequencies on at the same time. Down on the left, these are I call these mushroom plots because they look like mushrooms to me, but you can see the formation of the cat that goes on. There's the spin 7 halves, and then we do things like we project into a spin half subspace. So we want to be able to show scaling principles. So we're able to work with a spin 7 halves nucleus. We can work with all levels, or we can restrict the dynamics to sub-levels to be able to study scaling terms. And then up here, it's complicated, but we do these multi-tone pulses, and then these are all derived by greedy algorithms like GRAPE to be able to figure out how to make it work. And we're able to do pulse control to rotate. Remember what I said, that we don't just make the cat aligned with the external magnetic field, but we can pick any axis we want, and that comes out of a rotation term. So we're able to rotate states on the Bloch sphere, and we're also able to twist them. Okay, and then these are the kinds of effects we get. So the Givens rotation is kind of like one rung of the ladder at a time. Go up one rung at a time. And so, Givens rotation, if you look up, I think there's a Wikipedia article, it's just, you have a multi-level system. A Givens rotation is like a qubit type rotation on 2 levels, then you do the next. So if you go up a ladder, you do a Givens rotation to make a NOT gate, then Givens to the top. And that's what we don't do. We turn everything on. I don't have time to go into it, but we also have this, what we call a snap gate that takes place in the system. And so it turns out that we're working with microwave frequencies. We know the phases of all the different fields, and our snap gate is a way of recalibrating the phases for all the, we have this, ability to control the phase to make it jump to a different phase during the operation. And so we use this resetting of the phase of the microwave field to be able to do stuff. And then over here, these tables are just showing the evolution of the state. So it's all from the experiment, and it numerically validates that we're making pretty good cat states out of the system. What we do, we compare with, on one column, the Givens rotation approach, and then the cat state by one-axis twisting. So we do the experiment in both ways, and we find that if we do this whole, climb all the rungs at once, we get better results than if we did it by going up one rung at a time, Givens rotations. Okay, and then this is, now, my student Pragati and I prepared the slide. I didn't change it yet, but I don't like to call it continuous variable cat states, even though the literature talks about continuous variable, but you got the idea that I'm picky about that term. So what we say is continuous variable is really oscillator cat states on the left, and then cat states on the right. This indicates our control. that we're able to go to subspaces. And then the parity oscillations are ways of just measuring the fringes. So remember, the two coherent states in a phase space diagram has fringes. They manifest as parity oscillations. We measure those. We do our theory and experiment. We get to the 100% agreement. So the system is really isolated and very beautiful to use. And that's it. Thank you.